Hello, everyone. I'm Jesse Hoogland. I am the executive director of Timaeus. We're a nonprofit researching AI safety, much like everybody here, no surprise. Specifically, we work on something called singular learning theory, and we study applications of SLT to interpretability, alignment, and other areas of AI safety. So my plan for today is to walk you through some of the basics of our research agenda. I want to talk about where we're headed, the kinds of projects we have in mind for the future, some level. At a very high level, the question I want to answer for you is what could learning theory and the science of deep learning actually contribute to AI safety? What would it look like if this were successful? Okay, so the talk is called Singular Learning Theory and AI Safety. We all know why we're here, right? We're here because AGI is coming. Some of us probably think it's closer to the lower end of the scale. So we're on a timeline. We have to figure out how to make models safe. Now, in particular, two trends that I like to point to as a source of concern are, first of all, the scaling laws. This is an empirical phenomenon where we observe if you train models on more data, you train them on larger parameter counts, and for longer, you're going to end up with more capable models. More capable in the sense of lower loss on your pre-training objective or whatever other objective you have. Now, on the other hand, we have this striking observation that performance on any specific downstream task is much harder to predict, right? Like this is the phenomenon of emerging capabilities. We don't know where that performance improvement is going to come from. And when you combine these two things together, the certainty, near certainty that capabilities are going to come, we don't know where, that's the source of uncertainty and tail risk. And I think it's worth taking seriously. Can we understand better what's going on here? Can we understand where we're headed and how to deal with these surprising emerging capabilities? When you find yourself in a situation like the one we find ourselves in, I think it's sometimes useful to take a step back and ask, how did we get here? And I think we can trace it back to around 2011, when deep learning really started working, right? With AlexNet, computer vision was the first domino to fall. This was an empirical success. And we found, oh, you make the models bigger, you train them on larger data sets, it works. In contrast to what the theory at the time predicted. Right? Classical learning theory predicts large model, you should overfit, it shouldn't work. So we have this empirical success, and at the same time, this theoretical mystery. And that sets the stage for the modern deep learning revolution and the predicament we find ourselves in today. We're finding now, at least in my view, that some of these empirical techniques are starting to break down. So we're starting to see failures of our current alignment techniques at scale. Right? Recently, reward hacking has been one of the big ones. A while back, it was sycophancy. We don't actually know reliably how to steer models through our deep learning-based approaches to alignment and safety. There's mysteries here that we don't understand, and as a result, we're dealing with issues that are no longer vanishing with increasing scale. Maybe we can solve this generation of issues, but we don't have the certainty that we can continue to make models safer just by doing the same empirical thing we've been doing to date. So today we're going to go through the relevance of learning theory and science of deep learning through several stages. So I'm going to start by arguing that many problems in safety bottom out in scientific questions of understanding deep learning systems better. If we understand these systems better, maybe we can turn that into new practical tools for interpreting them more reliably and linking that information to alignment techniques. We'll take a look at singular learning theory. We'll start with some of the foundations of the Bayesian theory that SLT comes from, and I'll introduce some of the basic ideas and core takeaways of SLT. Then we'll look at this question of generalization. Why do networks generalize as well as they do? Where does that come from? And how might we understand this better? I see interpretability as being the science of understanding generalization and how model internals give rise to this generalization. Finally, we'll look at the role of the learning process and the relevance of understanding the learning process for developing better alignment techniques. Let's start with science and safety. So first, I want to introduce the idea that alignment nowadays is much like alchemy. Okay, so you have your cauldron, right? That's your architecture. You throw in some reagents, that's your data set. And then you start stirring. You apply fire, and all of a sudden your reagents start combining in chemical reactions that form, at the end, algorithms. Right, so here's uh, the stark difference between alchemy and, let's say, alignment, which is alignment actually works, or I should say deep learning actually works, right? We actually can just mix a bunch of data together in these cauldrons and get capabilities out on the other side. Okay, so this empirical approach, what's going on here? Now, most importantly, I'd say the difference between deep learning systems and earlier systems is this fact that they're able to learn algorithms. That sets them apart from earlier kinds of learning machines. So for example, linear regression, Gaussian processes, or clustering, k-nearest neighbors. These existing techniques from statistics and data science will never learn an algorithm. They'll never learn to sort a list, for example. In contrast, if you look at these recent papers from Anthropic and others, you find very clear evidence of models learning structured representations, computing on them in rich, sequential ways, all the hallmarks of conditionals and control flow and other algorithmic motifs that we talk about in computer science. Okay, so what is the nature of these algorithms? What's going on here? This is important for safety because ultimately it's the algorithms models learn that determine how they behave and generalize. Capabilities are rooted in the internal structures models acquire during training. So are goals, values, and other things that we would like to align them with. Okay, so alignment is currently this empirical art of alchemy of mixing data sets in cauldrons with fires. Now, of these three ingredients, these three inputs, which is the most important? In my view, it's the data, right? You can train the same algorithm, the same architecture on two different data sets. You'll get radically different behaviors out the other side. Or I can train different architectures on the same data set, and I'll often converge on very similar representations and ways of processing the data. So somehow data is fundamental here. It's fundamental both to capabilities, pre-training, chain of thought RL, and to modern alignment techniques. All of our current alignment techniques look like take the same deep learning techniques and just change the data. So for example, if you train next token prediction on internet data, you get pre-training. If you do this on example demonstrations, maybe from Wikipedia forums or other data sets that have this helpful personality, you get instruction or safety fine-tuning. If you do reinforcement learning against a binary correctness signal in the form of a formal verifier, that's chain of thought RL, that's the basis for reasoning models. If you do this instead against a specification, so I should say against a reward model trained on binary human preferences, now you've got RLHF, RLAIF, and these first generation alignment techniques. If you modify the training data based on some data curation rules, you get these synthetic data loops that are involved in training state-of-the-art models like 5.4. So this is how you eke the most performance out of models trained, small models. You train them on highly refined data sets. But if you do this on a data set of moral principles, a specification of human values, as in constitutional AI, or deliberative alignment, that's the current state of the art in alignment. Right, so at the end of the day, all of our alignment techniques, they look like just do deep learning on different data sets. So maybe we should understand how this process works, how data determines model behaviors out the other side. So what's going on here? Well, the key idea that we're going to look at in this talk is that maybe the answer is in the loss landscape, in the geometry of the loss landscape. The loss landscape is where these three ingredients come together, the architecture, the optimizer, and the data, to produce the final outputs, final models we end up with. So if you understand this geometry, maybe you understand this full picture. I've stretched this map out. So before we had data to algorithms to behavior, and I've just put this in a two-dimensional chain. So if this is how we align our models today, if this is how we program them, what's wrong with it? What's wrong with this approach? Well, I'll highlight two problems. Well, the problem in my view is that this process is implicit and underspecified. Let's focus first on the second half, the problem of generalization, as I'll call it. Right? Two algorithms can behave very similarly in pre-training. They can achieve near the same loss on my pre-training objective. Nevertheless, if I now evaluate them on some out-of-distribution data set, their behavior can radically diverge because they've learned different algorithms. So, when we're talking about things like deceptive alignment and we're trying to disambiguate which model is deceptive versus which model is actually properly aligned, trying to tell the differences in terms of this out-of-distribution generalization behavior, I would say that's the aim of interpretability. Interpretability is really about understanding internal structures to a sufficient degree that we can predict these kinds of properties, that we can disambiguate high-level properties like deception. So this process is underspecified in the sense that your training data is compatible with many different algorithms. Not all those algorithms are algorithms you want. So our techniques, they simply do not have the power to resolve those differences. The interpretability is about understanding where model behaviors, where generalization properties come from in model internals. Now let's look at the other half of this picture, learning, the problem of learning. So the problem with learning is that, in general, models are not even going to learn an optimal solution according to my specification. There are simplicity biases baked into the learning process that mean that my model might not actually learn to adhere with the specification I've given it. Our specification is loose, it's weak. It's not a hard set of constraints on the model. And I see alignment as being about developing tools so we can actually turn constraints on generalization behavior and on the algorithms models learn into interventions on training data. Okay, so can we go backwards through this process? Can we go from behavior at the other side to developing techniques ultimately for steering training data to align models more robustly? As we've seen here, many of these problems that have to do with we don't know what kind of model we're going to get, we might get a dangerous model, are really due to fundamental problems, scientific problems with deep learning being implicit and underspecified. So if we understood scientifically better what's going on, how the learning process chooses the final algorithm that the model ends up with, how that algorithm generalizes out of distribution, we might make progress on these safety problems. That brings me to SLT. We're going to go into the weeds a little bit. I'm going to set up some definitions and some basics, and then we'll zoom out and see how SLT gives us a handle on starting to answer some of these questions that I've just posed. So first, the question I want to start with is, what is learning? I'm going to take a Bayesian approach here. So we start with a prior distribution over hypotheses, H in squiggly H. We have a space of hypotheses. We're trying to figure out which of those hypotheses is best for explaining some data set D sub n of n samples. So our data set is drawn from some unknown probability distribution, Q. This is the true distribution, the data generating distribution. And we want to find the hypothesis that is closest to modeling Q. So we do this with a model. A model assigns a probability to some sample for a given hypothesis. You can combine these together into a likelihood. It's a probability of a data set given hypothesis. And then we end up with a mapping from a prior to a posterior with Bayes' rule. Now, the first modification I want to make to this definition of learning as Bayesian inference, is to recognize that in practice, we're always dealing with a parameterized Bayesian learning problem. We don't have abstract weights. We actually have some real-world implementation of a model where we identify hypotheses with numbers, right? Vectors in RD, the weights of a neural network. So in practice, we're always dealing with parameterized model classes. Now, the next refinement we're going to make to our definition of learning is we're going to study a certain simplifying limit. So what happens in the limit where we sample lots and lots of data? What I've done here is rewritten this in a form to emphasize the link to machine learning more clearly. I've just lifted up this posterior, the likelihood into the exponent. So now I have a L sub n, which is like it's a loss, sometimes called empirical risk. If I sample lots and lots of data, then what happens is my posterior is going to clump more and more around some optimal choice of weights. Under some assumptions, it'll look more and more Gaussian, more and more sharply peaked. And at some point, what we're doing is really no longer modeling a distribution, but we're just finding a single best choice of weights. We've seen infinitely many samples. In this case, my problem has reduced from inference, from finding a probability distribution, to finding just a single choice of weights, finding the W star, the optimal weights. And this is empirical risk minimization, maximum likelihood estimation. This comes with a major caveat, which is that these assumptions in practice don't hold for neural networks. We'll come back to that point in a second. Okay, so that's definition one of learning as inference. Bayesian inference, which reduces to this problem of trying to just minimize the loss. Now, I actually lied to you. There were two kinds of learning hidden away in this formula. There's Bayesian inference, which we just looked at, but there's also this second form of learning, which we call model selection, which is about finding the right architecture, the right model for the task at hand, right? Because implicitly, there's a dependence on your architecture in here, on your space of weights, squiggly W. As before, you can actually set up a Bayesian learning problem for this higher level problem of finding the right model class. I've got this hierarchy of Bayesian learning processes, both within a model class and at the level of different model classes. You can do a Bayesian update to find the right model class. Similar to the case in inference, if you sample lots and lots of data, this problem simplifies. So you're no longer doing this complicated meta Bayesian update. What you're instead doing is now just trying to find the choice of weight space, the choice of architecture that minimizes not the loss, but this free energy. Okay? And then we pick out a single model class, and that's what we're going to do learning in. Again, with this caveat for singular models, non-singular models. In particular, a seminal result from classical learning theory shows that the limiting form of this free energy simplifies to some term that involves the loss at your optimal choice of weights within this model class and some complexity term. But you want to balance the expressivity of your model class, so the number of parameters, D, against the fit it gives you. If it has too many parameters, you expect that it'll be able to overfit. So you want to penalize this tendency to overfit for non-singular models. So two forms of learning individual weights, which reduces to finding the weights with the lowest loss, and learning model classes, which reduces to finding the model class with the lowest free energy. What is internal model selection? Well, I mentioned this caveat, right, that these results hold only for non-singular models. Well, what is a singular model? Real-world models are singular. That means one of two things. That means they have non-isolated minima. There's not a unique global minimum. They're usually many. They're usually connected sets of minima. Right? I can perturb my weights without actually changing the loss I achieve. And the second key point is that the Hessian in general is non-invertible. So this again corresponds to the fact that there are directions in the loss landscape where the loss doesn't increase if I move it in that direction. As it turns out, this assumption that models are not singular is everywhere in the classical literature. And as a result, because deep neural networks don't satisfy this property, all these classical results break down for deep neural networks. They just don't apply. The classical theory is not a theory of deep neural networks. But we can make progress. So that's what singular learning theory does. Watanabe, the founder of singular learning theory, showed that you can, this is not due to him, but what you can do is you can recast the problem of doing Bayesian inference, so finding the right weights, as being about finding the right subset of weights. Okay, so we partition our weight space into different regions, different phases. Now what we're going to do is we're going to ask not which weight gets the most probability, but which region of weight space gets the most probability. Similar to the case with model selection, you can reduce this in some limit to the problem of trying to minimize a free energy associated with each of these regions. So now you're trying to find not a single weight, but a region of weights. And Watanabe gave us this asymptotic form for that free energy. So it involves, again, this term that first depends on the number of samples times the loss of your best choice of weights. But now we see that the complexity term, it's no longer d over 2, it's this other thing, this lambda, we'll call the local learning coefficient. So what you're really minimizing in a singular model, if you're doing Bayesian inference, it's not the loss directly, but it's this modified loss that involves trading off your performance loss against this complexity term, this variable complexity term. And that trade-off depends on the number of samples. So if you sample more and more data, it can change. And your posterior no longer smoothly concentrates around one choice of weights, but it can in general jump from one region to the next, all those phase transitions. So what we see here is really an implicit form of Occam's razor that's automatically satisfied for singular models. Okay. So as we saw in the regular case or the non-singular case, the complexity metric, this complexity measure is constant. It's non-variable. It only depends on the overall size of your model class. In general, for neural networks and other singular models, complexity varies even within that model class. Different regions of parameter space have different complexities. So you're finding the right level of complexity for a given data set. This is what we call internal model selection. Model selection that's internal to a specific model class. And that's the third form of learning, which I'll leave you with for now. Okay, so what do we see here? We saw that what neural networks are really minimizing in a Bayesian frame is not the loss itself, but this hidden trade-off between loss and complexity. The main form of inductive bias in Bayesian setting comes from this complexity term lambda. And we'll get into what lambda really means in a second. What we're seeing here are a bunch of close parallels between the development of learning theory and the development of physics historically. So physics started with, say, classical mechanics, which is about understanding the flows and minima of energy. You have a pendulum, where does it relax? What state is the energy minimized in? If you understand that minimum and the local behavior in the vicinity of that minimum, that tells you essentially all you need to know qualitatively about that physical system. On the learning theory side, the equivalent of energy is empirical risk or loss or negative log likelihood. And all of the classical theory focuses purely on what are the properties of minimizers of the risk. What comes after classical mechanics is thermodynamics. So thermodynamics studies heat. Heat is this hidden form of energy exchange where particles are bouncing around and exchanging energy with some mechanical system, and you can't actually measure those hidden degrees of freedom. So what you do instead is you describe the macroscopic system as some trade-off between the energy that you can measure and this entropy. You're minimizing the free energy, this modified energy, rather than the energy alone. In SLT, we get something analogous, right? There are these hidden degrees of freedom. In particular, there are hidden missing degrees of freedom. And that means that what you're really minimizing is this trade-off between energy and complexity. I should say loss and complexity. Now, what comes next after thermodynamics? Well, in the case of physics, we go on to statistical physics. So statistical physics, really the study of internal structure in systems. It is a step that comes after thermodynamics that tells you about what's going on inside of the system. Can you probe, for example, the crystal structure of some solid? Can you understand what's going on microscopically based on purely your macroscopic observations? So similarly, we've been working on extensions of SLT that try to get into something more like statistical physics that tells you about internal structure, that does interpretability based on the same kinds of ideas as in statistical learning theory, so statistical physics. What comes after that are more exotic things. Right? You get condensed matter theory, where nowadays physicists, they don't just describe systems, they're able to engineer new materials. they're able to design exotic materials that have never been encountered before in the wild with the precise properties that they want. And maybe the hope here eventually is to do something analogous for neural networks. Can we develop that level of control that we can actually engineer the precise properties, goals, and values of these systems? And that brings us to generalization and interpretability. So I want to start with a hypothesis, scientific hypothesis that, if true, will give us a new handle on understanding what's going on inside of models. We call this hypothesis structural Bayesianism. So the idea is the following. Maybe the algorithms the model learns cast a kind of shadow in the local loss landscape. If you can measure that shadow, and you can invert this mapping, that gives you a tool for inferring or reconstructing the algorithms the model has learned. So maybe it's easier, in fact, to not interpret the model at the level of the algorithms directly, but you should interpret it at the level of geometry and then reconstruct the algorithms from this information. And that's the basis for using this hypothesis, grounded in SLT, which again is a theory of the role of the geometry of the loss landscape and of minima in the loss landscape for developing techniques for interpretability. So I'll walk you through an example of this kind of correspondence between geometry and algorithmic structure. And that's called the local learning coefficient. So going back to this lambda from before. Right, so in this formula, what is lambda really? I said it's a complexity measure, but what is this number really? Well, it's a number that has two sides to it. So on the one side, it measures something about geometry, geometric degeneracy, which I'll define in a second. And on the other hand, model complexity, algorithmic complexity. This is going to be the zeroth order version of this hypothesis, this correspondence between structure and geometry. Let's start with geometry. So what I'm going to do is take some loss landscape, and I'll take a minimum in this loss landscape, and I'll ask how many solutions are almost as good as that minimum. Right, so for some tolerance epsilon, what volume of weight space can I access? What's the area, in this case, of this blue surface area? In general, what you find is that the volume will scale like the height, epsilon, to some power lambda, where lambda is this learning coefficient. So the learning coefficient is the volume scaling rate. It tells you how quickly volume scales in the loss landscape. This is the highest order contribution to the volume at that point.
30 minutes.
Let's look at a few examples. So first, if you have a paraboloid, so x squared plus y squared, that's something that looks like this. For paraboloids, the learning coefficient is maximal. In this case, d is 2 dimensions, so 2 divided by 2, it's going to be equal to 1. But you can have something more exotic, like x to the 4th plus y to the 4th. In this case, it's more square, and lambda will be smaller, it'll be equal to a half. Or something more exotic still, x to the 4th times y squared. Now we have these intersecting values. Now lambda is 1/4. Now something I want you to observe is that for these last two examples, if you look at the origin, the Hessian is the same. It's the zeros matrix. So second order information in the Hessian, standard measures of curvature and flatness, can't distinguish between these two. What SLT is telling you is that actually the most important contribution to the volume does not come from curvature, it doesn't come from second order information, it comes from degeneracy. Degeneracy is the number of ways that I can vary my weights without actually changing the loss. Yeah.
Sorry, and I meant the why volume.
We'll get
You repeat the question.
why. Okay, so the question is, why is volume the thing we want to be measuring? I'll get to that in a bit. So if I don't answer that, you can prompt me again. Okay, so on this, here we're seeing the learning coefficients as this measure of geometry. That doesn't tell us why we should care about it. Another perspective on the learning coefficient is that you can approximate it using this formula. What this formula is telling you, you can approximate the learning coefficient as the average increase in loss from some starting choice of weights to nearby points in the neighborhood. If I perturb the model, how much does the loss increase on average, where my perturbations are sampled from some local posterior? So it's measuring something like fragility, right? If the model is very fragile, then a small perturbation is likely to increase the loss. That's the geometric side. What about the algorithmic side, the model complexity side? Well, again, for a non-singular model, for a regular model, the learning coefficient is just equal to the number of parameters divided by 2. In general, if your model is what's called minimally singular, then the learning coefficient will be like an effective dimensionality. If there's a parameter you're not using, you can set that parameter to an arbitrary value and it doesn't change what you're actually doing, then the learning coefficient will be a half smaller. More generally, you can get these contributions from terms that look like x to the fourth or x to some higher power, where you'll get a fractional learning coefficient. So it's somehow richer than just an effective dimensionality. There's more going on. And I want to walk you through a few examples where we can see this link. Consider a deep linear network where the task is to learn a linear transformation of input data. So we're given x, y pairs, and we want to learn the transformation x to y. However, we're going to parameterize this in a weird way using a product of matrices, a times b times x. And so a product of matrices isn't more expressive than just a single matrix, but the geometry is more interesting and the dynamics are more interesting. In particular, suppose that you're trying to learn this matrix, one in the top left corner with zeros everywhere else, and you set A equal to the same matrix. Now, because this is low rank, you actually lose parameters in the second matrix. I can set B1 and B2 to arbitrary values, and I'm going to get the same behavior out the other side. So this means there's a hyperplane of weights that all encode the same function. There's a degeneracy in the loss landscape that corresponds to me using fewer degrees of freedom to me implementing a solution that's lower rank. A slightly more interesting example comes from dead ReLUs. So we've got a ReLU neuron, right? It's just some matrix times ReLU of some matrix times x. Consider what happens when my pre-activations are always negative. So for example, I've set my bias to a very high value, so I can never activate this neuron. But what happens then is that the outputs will be 0. And so now there's a free row in my B matrix. Again, the learning coefficient is going to be lower than this. There are now directions in the loss landscape that can vary because I'm doing something simpler, because I'm not using the full expressivity of my model. However, if I push the model past this point, and now on some inputs it activates, on some inputs it doesn't activate, now I'm using that row of values again. So I lose that degeneracy. If I push it even further, maybe I set the bias to a very large negative number. Now it's always activating. Now the ReLU is no longer nonlinear. And so I'm really back in the deep linear case from before. I get the same kinds of symmetries and degeneracies as in that case. So what we're seeing in these examples are ways in which if I'm implementing a simpler function, I'm using less of the expressivity of my model, that's going to show up as more volume scaling in the loss landscape. So we talked about effective dimensionality. More generally, we expect that the learning coefficient reflects many other properties of the algorithms that models learn. In a particular setting of noisy Turing machines, you can show that the learning coefficient reflects how error correcting your solution is. Suppose your model makes a mistake internally, but still produces the correct output. That's actually reflected again in the geometry. Other properties, possibly like modularity, might also be reflected in the learning coefficient. So if you can measure this complexity metric, it tells you something about high-level properties of the algorithms your model has learned. Okay, so that's the learning coefficient. What does that have to do with generalization? So this is the real reason we care about the learning coefficient. The reason is that in the Bayesian setting, the learning coefficient is the leading order contribution to what's called the Bayes generalization error. This is the main form of generalization error that we care about in the Bayesian setting. It's defined as the KL divergence between the true distribution, so the distribution that's generating the data in your data set, and your posterior predictive distribution. So the posterior predictive distribution is the prediction that I would make if I use all of the models in my posterior, and I use them to weight the prediction of this new sample. This is a theoretical object that you can't actually realize in practice, but in theory, in the Bayesian theory, it's some of the most important kind of generalization error. And again, because the learning coefficient is constant for regular models, that's why you predict that regular models should overfit if they have too many parameters. But because the learning coefficient is less than, in general, the number of parameters divided by 2, generalization can be much better than you would expect just by looking at the apparent parameter count. So this is the answer to, at least in a Bayesian setting, why neural networks are able to generalize in distribution. In distribution, generalization is dominated by the effects of the local learning coefficient. Ultimately, we care about more than just in distribution generalization. We want out of distribution generalization. So how do we get to that? No, that's not going to help. This is where we introduce susceptibilities. So I'm going to go over this kind of shallowly. If you're interested, you should ask me in more detail. Susceptibilities you can think of as a kind of derivative of the learning coefficient. How much would this learning coefficient change? How much would the generalization error change if I make a small intervention on the training data? For example, let me upweight GitHub data. I increase the concentration of GitHub data in my pre-training distribution. How much would the structure in my model respond to that, increase or decrease? That's what the susceptibility is measuring. What this is, if you plug in the Bayes generalization error, it gives you the first order expected change in generalization if you had changed the training distribution a little bit. So this is a local first order approach of the question of out of distribution generalization. If you're actually going to make your model go through a distribution shift. So to put it all together, what we're starting to see here is through SLT, we see this link between sensitivity analysis and weights. How much does my loss increase under typical perturbations to my model? What's the LLC? And sensitivity in data. How much does the behavior change if I shift the distribution the model is trained on or evaluated on? These questions are the same. They can be linked through this perspective based in SLT. We see that in distribution, again, is solved for Bayesian systems. And we see the starting step for a first order correction to this if we're going to change the data distribution. You can imagine that you can continue this series and try to come up with more and more nuanced corrections to generalization as you consider larger and larger distribution shifts. So generalization is rooted in the sensitivity of the model, in the complexity of the algorithm the model has learned, and is visible in geometry. It's visible in the volume and volume scaling rate associated with your models. What does this mean in practice? Okay. This story is all nice and good, but it doesn't mean anything if you can actually measure these quantities. So fortunately, it's actually possible to estimate quantities like the learning coefficient, like the Bayes generalization error, like these susceptibilities. And the way to do that is two things, really. First is we're going to use stochastic gradient longevity dynamics to estimate this expectation value. What this looks like is I'm going to sample a bunch of points in the neighborhood of my local minimum, in the neighborhood of my checkpoint, by just taking SGD steps, adding a little bit of Gaussian noise, taking SGD step, adding Gaussian noise, and iterating this. That'll give me samples. And then if I make sure that those samples stay close to my weight, I ensure that I sample the local geometry by adding this localization term. Now I can faithfully and at scale sample what the geometry looks like for these models. Gives me a way to turn this theoretical story into a set of empirical tools. And this is what it looks like. You do lots and lots of experiments. Thanks, Max. Yeah, you ran lots and lots of traces. So you burn lots and lots of compute to sample points in the neighborhood. In some cases, we actually have the ground truth. So we know that it's possible to sample this, to sample the true value accurately. That's what you see on the right-hand side for deep linear networks where we have the ground truth value. you can see that our estimates are actually well calibrated. Okay, and that brings us back to safety. So I want to talk about SLT of the SLT, or for the SLT, for the sharp left turn. Right, the sharp left turn is this idea from Nate Suarez that under distribution shift, different capabilities, different algorithms inside of the model can generalize differently. It might be the case that one capability survives while another capability breaks. You change the distribution that the model's evaluated on. In particular, we might suspect that certain capabilities, power seeking, deception, the things that instrumental convergence talks about, are deeper in the model. They generalize more robustly across a wider range of distribution shifts, while alignment properties, values, goals, the kinds of things we want models to pursue, are more shallow, more liable to break across the distribution shifts. This is not a shallow perspective on the problem. I think there's a real sense in which you could formalize this problem and talk about the depth of different capabilities, talk about how they generalize differently. The kinds of questions I'm interested in here are, can we expand SLT, which is currently a theory of Bayesian statistics, to a theory of in-distribution generalization in SGD? Can we advance SLT to a theory of out-of-distribution generalization, as I started to hint at? Can I do both of these at the same time? Can we promote generalization, which is usually thought about as a scalar? It's a loss, it's a single number, to a richer mathematical object, tensors. We promote it to something that actually reflects the algorithmic structure inside of the model. Mathematically, this might actually give us a principled way to link interpretability to generalization behavior. How deep are different capabilities and values really? How do you measure this? How's the depth of a capability related to the depth in the data set? The percentage of explained variance of that particular pattern in the data set at large. And how's this related to physical depth in the loss landscape and the structure in the loss landscape? And how does this relate to when the model learns it? These questions, I think, can all be made precise and studied rigorously using this kind of perspective from SLT, and then turned into practical tools and methodologies for intervening in what the outcomes of the questions are. So the perspective I want to leave you with here is that interpretability, really what we care about is how models generalize. We don't care about all of the particular minutiae and details of what's going on in the model. And maybe we can actually get at these higher level generalization properties through this geometry grounded approach, which gives us, through the theory, a principled link with the object that we really care about. Brings us to the last section, learning and alignment. So previously I started with a hypothesis. I want to introduce another hypothesis, and this time it's what we'll call the S4 correspondence. So S4 for 4 different kinds of structure. The idea before was that the algorithms the model learns are reflected in geometry. And so if you can read that geometry, you can reconstruct the algorithm. The idea now is, well, where do those algorithms ultimately come from? Where does this geometry ultimately come from? Well, it comes from the training data. Right? Geometry is the thing that sits between your data and the thing that the model learns at the end. So maybe the application here is if we can reverse this arrow, we can go from properties of algorithms to constraints to interventions on training data. In particular, the S4 correspondence stands for 4 different kinds of structure. It's the idea that statistical structure in the training data determines the geometric structure in the loss landscape, which together with your optimizer determine the structure of the learning process, which picks out the final weights in those algorithms and behaviors that your model ends up with. So similarly to the case of structural Bayesianism, where maybe we can invert this relationship, might it be possible to invert this relationship? Are these arrows faithful enough that we can go backwards? I'll start by giving you an example of what this looks like for the learning coefficient. We already can see some kind of link between these different layers. So we saw how simpler patterns, in the sense of learning a deep linear network with a lower rank, or having a dead neuron, or having an always activating neuron, these show up as a model being more degenerate. They occupy more volume. Because they occupy more volume, they are easier to find. More volume makes a model easier to find, and so they are preferred by your learning process. This can be made precise in SLT by looking at this free energy, which quantifies exactly how much this preference shows up. And finally, we saw that a more degenerate model is one that generalizes further. Intuitively, this makes sense. All other things being equal, you want the model that's compatible with the data, that's simplest. It's the one you expect to generalize the best. But you can, again, make this precise and quantitative using SLT. And so we're starting to see links between these different layers. Can we do more? Well, we expect this link to be true for arbitrary kinds of learning processes. The theory tells us about the Bayesian learning process, but we also expect it to be true in general for stochastic optimization, SGD, ADAM, any kind of optimizer you would choose, even zeroth order methods. Okay, so what does the Bayesian theory say? Well, Bayesian theory gave us this internal model selection principle. What you observe in practice is that the posterior can shift, it can jump from one region to another, if the trade-off between the free energy here and the free energy shifts with the number of samples. And jump through this at a slightly higher pace. So we have this very precise prediction about what learning should look like for Bayesian learners due to the free energy formula. In practice, you actually observe this empirically. So for toy networks like deep linear networks or the toy model superposition, you actually observe learning, even for models trained with SGD, as broken into different stages that correspond to Bayesian phase transitions. So we have some empirical evidence here to expect that this perspective from the theory tells us things about real-world models. What about more interesting models, right? Well, that's where we started with developmental interpretability, or definterp. Here, the idea is that if you understand these phase transitions over the course of training, maybe that's enough to understand the model internals of the final model. You understand the sequence of steps that build something up, that's enough to understand the final model. And in some cases, it might be easier than trying to understand each weight individually at the end of training. And so we've worked on through a series of papers on trying to start fleshing out the correspondences between these different levels. What you find for simple two-layer transformers trained on natural language is that learning looks very simple when you look at it from the perspective of the loss. It looks very homogeneous, mostly. But if you look at this learning coefficient, you can divide learning into a series of developmental stages and, in fact, interpret these. So models first learn bigrams, then they learn n-grams and skip n-grams. They learn the induction circuit in two parts, and they finally converge. So in practice, we do observe the same kind of stage-wise development predicted by the theory in practice. Okay, so what we see here is that these different statistical patterns, bigrams, n-grams, induction patterns, give rise to different developmental stages. The model learns the simple things first, followed by successively more complex things. This can actually be quantified and measured using these measurements from geometry in an unsupervised way before necessarily knowing what they mean. And follow-up work shows that you can actually refine this perspective to also say something about which attention heads specialize to which different roles. The different circuits that show up. So not just the induction circuit, but other kinds of peak circuits. So we're starting to see for these small language models that here too, there's this correspondence that we can start to flesh out. Most recently, we've been looking at these susceptibilities in practice. So again, susceptibility is this derivative of an expectation value. What you can do is you can measure this for a bunch of different data sets and a bunch of different attention heads or components of the model. This gives you a matrix, and you can, well, with a matrix, you can apply SVD, you can apply principal component analysis. And if you do this, what you get is a principled set of couplings between patterns in data and structures in the model. So this lets you actually recover in an unsupervised way all of the structure we previously discovered in these models. You can discover that The most important kind of pattern in the model is word boundaries, followed by the induction circuit. You can automatically differentiate all the heads involved in the induction circuit from the rest, followed by this other Deek circuit. You can identify those heads from the rest of the heads. So using these more nuanced measurements based on geometry, we're starting to get a more nuanced understanding of the structure inside of these models. And the hope is that you can potentially flesh this correspondence out in much more detail, right? Mathematicians have different ways of talking about all these levels. How deep can we go? How sophisticated a correspondence can we get? Say one word about SLT for bias and convergence. I'll just jump through this and wait for the car to. So, as in the case of generalization, understanding learning better could actually give us a handle on real-world safety relevant problems. Is it really the case that the deceptive alignment is simpler? I don't know. This is often offered as an obvious assumption. It's not obvious to me that it is actually true. The same goes for all the other kinds of biases that instrumental convergence talks about. Are these things actually preferred by the posterior? Are they actually simpler and easier to find than values that we care about? What we're ultimately trying to get at is if the correspondences are sufficiently faithful, then we might be able to use this to turn constraints on algorithms into interventions on training data. Ways to choose training data, ways to curate training data, design curricula, and the like. And that brings me to the end of the talk. So here well, in 1 second, don't worry. We're not yet at safe AI, okay? We need to do more. So what's left between here and AGI? Well, we started with alchemy, but fortunately chemists figured out what's going on in these cauldrons, right? And we ended up with industrial chemical engineering. Maybe we can do the same thing for AI safety. We're starting to see the first inklings of what that might look like. Thank you very much. Like this?
Thank you, Jesse.